So, for this part we are going to do an experiment which was done way back a few hundred years back by Galileo. He was a very famous scientist, as you all know, from Italy, and he had devised a thermometer called Galileo thermometer. And the reason I am trying to show that, because we are now trying to look at how we can measure the temperature, which is the zeroth law of thermodynamics, using some of the concepts of molecular dynamics and simple simulation. So, let us look at now your screen. We are going to look at the experiment which is in your VMDL lab, which is called Galileo's thermometer, and this is a pre-recorded simulation. So, you will see some of the processes happening. First, let me make sure that you have higher magnification. Okay, that's good. And in this case, what you are seeing is on the left hand side, you have a almost like a tube, and there are a whole bunch of particles that you are looking at, and you will look at the expansion and the movement of these particles. So, let me first set the experiment. This is a model of Galileo's thermometer. Very thin tube which contains a liquid droplet. So, these sections, the green dots, are essentially showing a liquid droplet and enclosed in a gas sample, which is the blue particles, and you can probably not see them clearly because it's very small, but let me see if I can get better magnification for you. And so yeah, now you can possibly see the blue particle which are holding this particular top level, which is the green particles of a droplet. So, these droplet is going to move up and down based on the temperature positions. So, in order to see better part, you go to, if you look at, we can also now look at the steps that we are going to run. So, this is kind of the concentration. You can see all this gas concentration, and this green is the concentration of the droplet. But now, let us go to temperature, and you can see this is temperature here, because we are trying to do thermometer at certain times. So, we are going to play that simulation. So, now you can see that it is gone into a equilibrium position. So, if you look at the gas is at the constant temperature and pressure, liquid droplet fluctuates around an equilibrium position, and that was the fluctuation that you saw. And let us look at it again. So, here is fluctuation, but it is keeping the temperature and pressure constant, which is important for the measurement of the temperature. So, droplet is moving up and down, and with that the temperature graph to the concentration versus y axis. So, now let us look at the concentration. So, on the y axis, now you can see this is a snapshot that you can look at and record the temperature. So, now we are looking at the temperature of, let us say, on the y, this is the concentration, and the temperature is 0.09998, which is almost reduced temperature of 0.1. So, that is what we record. Now, we play it again, let it move, and the temperature of the graph sample is about to change. Return to the temperature graph. Now, let us go to the temperature graph, this case again, and then play it. So, now you will see the change in temperature. So, here is change in temperature, and that is now you are looking at this temperature graph, and if you look at the temperature here, you can see that how the location of these the droplet particle within that tube has gone down with the change in temperature, which you are looking here is almost like 0.5. And now, by calibrating and with this gas which is changing with the change in temperature, you can calibrate and create a thermometer, because again, as what we said is the law of gases, the temperature and the volume of the gas is related linearly. So, if you can calibrate that using the Charles law, this is what was Galileo's idea of creating the thermometer. So, if you look at here, let us go a few more steps, and if you look at the change in temperature, now it is coming to some kind of equilibrium, at 0.888989. So, it is still going down, it is not completely at the intended temperature of if you look at 0 between 0.5 and 1.0. So, this should be anywhere 0.75 or even 0.8. So, we are close to 0.8, but not 0.08 yet. So, we go further down, and now you can see this solid line coming up, which is gone into further down temperature. And if you look at here in the tube, again the gas has gone down, and this reduction in the measurement of the temperature is connected again linearly with the temperature. So, if I have to rewind this, you can see here I can calibrate it to 0.5, then I can go to 0.8, and then I can go to 1.0. So, 0.05, 0.5, 0.8 and 1.0, these are the three temperature steps that we looked at. And now, if you increase the temperature quite a bit, quite high, then you can see that in this entire tube, the gas and liquid, the liquid particle, the droplet has broken down into pieces, and then it has really become a mixture of the two ideal gases. So, this is an example that how the laws of thermodynamics, now with the equality of the temperature and the surrounding system, we are able to look at the droplet on top of the gas, and then by varying the temperature, the volume of the gas is changing, we let it equilibrate, and then you can come up with a particular location where now you can calibrate this whole tube, which is a rather large tube at that time when the Galileo was doing this experiment, not like the thermometers today, which are very small and tiny. With the mercury, we are able to do a lot of measurement. So, this is a practical application of again molecular dynamics using the laws of gas, ideal gas, and measuring temperature. So, we simulated that, and we proved certain ideas of Charles' law as well as some of the laws of thermodynamics. Thank you.